Saxon Advanced Mathematics, Lesson 43. Students, I'm excited. We're gonna start a fun topic today, and just so you know how much fun I'm having today, the Algebra 2 students, Abby and Micah and Kyle, they just got their first taste of trigonometry. They learned sine, cosine, and tangent. I told them my story about Oscar and Arthur, you know, Oscar jumping poor Arthur in the alley and choking him, and they learned how to use the buttons on the calculator. Yay, very exciting. So now you have an exciting day too in the world of trigonometry. But first I'm going to show you some things that you already know, because that's the best place to start a lesson, is by being reminded of something you already know. These are graphs of functions that we have looked at in considerable detail. This is a linear function, this is a quadratic function, and this is an exponential function. I was having a hard time spitting the words out. And here are some examples, right, of what they look like. Right? This is an example of what creates that kind of a line. Here's an example of that, and here's an example of that, right? So specific kinds of functions create specific kinds of pictures. And when we can associate the equation with a picture, it helps us understand better what's going on. So that's the firm ground on which we stand, the firm foundation. And what we're going to do is extend this concept to sine and cosine. Our trig functions, they get to have graphs too. How cool is that, right? That is awesome. So let's take a look at what their pictures look like, and I will give you spoilers. They're quite similar with some interesting and subtle differences, but sine and cosine are going to have a very distinct look. Not like these, but they're going to look a lot like each other. All right, so let's take a look at that. When we draw the graphs of our periodic functions, what we like to do is kind of extend the x-axis quite a bit. And then the y-axis, we keep it fairly short. And you'll see I've got my center kind of skewed, don't I, off the middle of the page. That's okay, you'll understand why once we get the hang of it. All right, this is still what we call our x-axis, although I'll give you more spoilers. Sometimes we call it theta, but we'll get to that. Either way works. This is still just good old y. And when we mark these off, we're going to be using our quadrantal angles, okay? This is where you have to start letting your mind bend a little bit. When we normally talk about sine and cosine, we're drawing angles on a grid, and we know this is 0 degrees, this is 90, this is 180, and this is 270, right? That's how we've been placing our triangles. And then we know that you can come around, and you can also call this a 360 angle. And if you want to get totally crazy, you can call this, what would this be, a 450? And this would be a, let's see, I add 90 to that, so it would be a 540. And then we add 90 to that, so this would be a 630. And then we'd come around again, and this would be a 720, right? You can keep going around and adding, increasing the circle. Well, that's basically what we're doing here. I'm just trying to get this organized well so you can see what I'm doing, all right? So this is our 0 degrees. This is 90, this is 180, this is 270, 360. Notice I'm just using these original values of our quadrants, right? And then I'm gonna, so that's one spin around, and then I'm gonna do the second spin around, 450, 540, 630, and 720. And then I'm gonna go backwards just a little bit. I'm just gonna go one spin backwards. So this will be minus 90, minus 180, minus 270, minus 360. Okay, so the values we choose to mark off on our x-axis are a little different, but they match up to the way we have been thinking about angles in this perspective, right? We're kind of shifting our perspective. That's where this gets a little line bendy, where these values used to go around in circles, and you know, they still do. We'll do problems like this. We're also taking them and stretching them out, and you'll see why. Now, that's the framework. Oh, and in the beginning, we're gonna mark our what we call the amplitude as 1 and -1. This is called the amplitude. Okay? All right. Now, what I've got handy is the chart we've talked about. This is our quadrantal value chart. Quadrantal angles is technically what I should call it, right? And we talked about this, it was quite a while ago. I think it was like lesson 29 or something. And we said that at these measures, which are the 4 corners of our grid, sine and cosine have very specific values. They range from 0 to 1 and then down to -1. This one starts at 1 and varies, right? We're not going to talk about tangent today. Poor tangent has these undefined values. That makes him complicated. So that's why we're not talking about him today. We will get to him, but he's just kind of a problem child. I'm sorry, tangent. I love you, but you're just difficult. So we'll get to him, but we're going to wrap our heads around these two first because they're much easier. All right, now look at these quadrantal angles. What we're going to do is we're going to plot these points. I'm starting with cosine. We're going to plot these points on our chart. Okay, so at 0 degrees, the value of sine is 0. Dot. At 90 degrees, the value of sine is 1. So I'm going to go up here. At 180 degrees, the value of sine is 0 again. And at 270, it's down at -1. Okay? Now, if we were looping our values, we see that 360 is like 0. So we would be back, 360 is the same as 0, so we would be back at 0 again. And then 450 is like 90, so we would be at 1 again. And 180 is like 450, so we would be at 0. You see what I'm doing? I'm extending this for like 2 trips around the circle. 630 is the same as 270, so we'd be at -1. And then 720 is like these guys, so we would be back at 0. Okay? So all I'm doing is plotting the points for our quadrantal angles, and then I'm taking a second trip around and using those same values for the higher angle measurements. Now, here comes the fun part. Now I'm going to connect the dots and try to make it smooth and curving. And what I've created is called the sine function. How cute is that? And even better, you guys, it goes backwards. And we follow the same pattern, and I could work this out on my quadrantal angle sheet to create all the similar angles. But we know it's just going to follow the same beautifully curving pattern. And this is called a periodic function because it has this lovely wave kind of feature. Pretend it's perfect, right? It's got this lovely wave feature that is distinctive of a periodic function, right? Isn't that awesome? And the way that we write this is we write y equals the sine of, in this case, we would say x, right? But we could also say the sine of theta. Either way works. Isn't that awesome? And I don't want to get into too much theory on this part of it, but I want to show you that if we want to do y equals the negative sine of theta, or x rather, we're talking about x. What happens is we just flip-flop the points like so. And so it starts at the same place, but then it goes down. So it's like the opposite, right? Isn't this sort of trippy and fun? Say yes. Right? So the two intertwine and make that really cool pattern, okay? Let's take a look at, this is sine. And now let's just look at how cosine works. We'll start with our chart the same way. We'll put in the ones, the amplitude of 1 and -1. Then I'll put in 90, 180, 270, 360. 720. I'm not going to write in all the numbers. And that's -360. Okay? And now we're going to do the very same thing. We're going to look at our quadrantal angles. And we're going to use those to guide where we put the dots. Okay. So cosine at 0 degrees, which is where we are right here, right? This is 0. Cosine starts out at 1. Then it comes down to 0. Then it goes down to -1. Comes back up to 0. And then 360 is the same as 0, so it's back up here. Okay, so let me just draw that much in for you. Cool, right? And so now we continue the pattern just like we did before. And what we're doing, remember, is we are extending a second time around, right? We're using those same quadrantal angles on the second trip around the dial and using the same values for them. And then likewise, we can go to negative land. And that creates this super smooth, slinky shaped cosine function. And we say y equals the cosine. This time I'll call this theta. Cosine of theta, and then we'll do the -1 in pink. Y equals negative cosine of theta. And we do the same thing. The points right on the line, the zeros, if you will, stay the same. And we just swing the extremes in the opposite direction. And then I connect. So satisfying. Beautiful, right? So there's everything you need to know about the cosine function. It is also called a periodic function, and we'll talk a lot more about this. But in the period from 0 degrees to 360, we can see that the function takes one full spin. It goes through all of its extremes, right? And so we call that a period. It's one phase where the cycle goes through all of its changes. And here's the same thing. This would be considered one period. Oh, I'm sorry. I made that one too small. It needs to go all the way to 360. Right? So let me just show you. Let me just make it a little brighter. There's one period of the sine curve. Notice it starts in the middle, goes up, down, and back. And then here's one period of the cosine curve. And it starts high and falls. Cosine is more of a roller coaster, isn't it? Well, I mean, I guess technically a roller coaster, you start out here, right? And then you climb up. So maybe I'm wrong. Beautiful. This is more of like a valley, right? So there you can see one period more clearly. That's why we call it a periodic function, though, is because it repeats the periods. Okay. And then the last twist that we're going to put on this today, we're going to put lots more on in the future. Don't worry. And we have just 2 problems to do. We can change the amplitude. if we want, I guess I can draw it out again. We can change the amplitude. If we want to say y equals 2 times the sine of theta, this number tells us the amplitude. That, remember, is the height. But here's the fun thing. We can draw it exactly the same. We just, instead of this being 1 and -1, we just write in 2 and -2. Sorry. Sometimes my hand just can't keep up with my mouth or my brain. And then these will be the same, right? This is 360. And we'll go up to 720. And then we'll go back to minus 360. And this is sine, so that tells us we start out here, and then we just go up and down and down and up, right? There's one period of the sine function, and then we repeat it just as we would on a graph go around a second time, right? And then we can do the negative ones following the very same pattern. Beautiful. So this is an example of changing the amplitude. And then another thing I want to show you that you need to know for the homework is, what if we have the negative and the amplitude? This is the -2 cosine of theta. Okay, we can handle it. This time it's theta here. I didn't put my x and my y. This is always y. This is theta or x. You can tell by the problem. It doesn't make any difference. It's just stylistic. We will put in our amplitude of 2 and -2. Again, I don't have to create any special size gap. Just labeling properly is all you need. 1, 2, 3, 4. 1, 2, 3, 4. I made this one a lot bigger, didn't I? There I had 720. And so 1, 2, I'll just do half a period down here. Cosine normally starts at the top, right? That's what we saw back here. Cosine starts at the top and goes down and back up. But this is negative cosine. So this inverts the curve, right? So that means I'm going to start down here and go like so. This will be one period, right? And then another period would look like this. And then here I would do the same thing. Okay? So these would be the solutions to these problems. All right. Let's see what John says. Write the equation for this sinusoid. I have to show you the picture. This is example 43.1. Okay. I have some sticky notes on my page. Don't be distracted by that. All right. So we're trying to figure out which sine this is, or which, we're trying to figure out the equation of this sinusoid. Okay, we know it's going to be y equals. Then the next thing we need to know is whether it's positive or negative, and which function it is. So let's look at it. Well, it comes out of 0. That is a sure sign of the sine curve, right? So this is a sine curve. Is it going in the right direction? Yes, it's going up. If it was sine and going down, then we would know, oh, it's a negative. So this is a positive sine curve. It's doing a great job. The only other thing right now we need to know is the amplitude. Oh, look, the amplitude is 6. So we put a 6 out in front of it. And then we just need to know what's there. Is it an x or a theta? It's a theta. So here's how we wrote that down. It's a cute little sine curve. It is not a negative. Theta is the variable John used to define this axis, so we use the same one. And then we noticed that the amplitude was measured at 6. So we just wrote that down. That's the right answer. Cute, right? And then the other problem is the very same thing. Okay, so let me bring it back. It being the book. Ah, it's tired. It doesn't want to talk anymore. All right, now we do the same thing. First we look to see, is it a cosine or a sine? Is it positive or negative? All right, it's coming out of the deepest valley, isn't it? So we know that must be a cosine because sine begins at the 0. So this is a cosine curve, but look, it's down at the bottom and it's going up. Usually cosine starts at the top and goes down. So we know this is a negative cosine curve. So I'm going to write y equals, then I'm going to put a minus sign and I'm going to put cosine. It's an x this time instead of a theta, so I put that in at the end. And then the last thing we need to check on is the amplitude. And I see 3 and minus 3 are written there, so we just write 3. The amplitude measures the difference, not the specific number. So you wouldn't necessarily put minus 3 there. I mean, it works out that it kind of looks like that, but what we're measuring when we measure the amplitude is the distance from that point to 0. And it doesn't matter if it's 3 or negative 3. It's just the distance, all right? So this is our answer. Y equals minus 3 cosine of x. Yay, got it right. All right, you guys, these problems are fun. Here are a couple for you to do. 7 and 8. If they're blowing your mind at all, do both of them. And that's good advice I would give you. I mean, I know as students you're not really looking for extra work, but when you're dealing with a new topic, it's worth a couple extra minutes to try a second problem and just drive your understanding a little deeper into your brain. But we're going to be playing around with these for quite some time. I hope you enjoyed them. I will talk to you next time. Goodbye.